equation for exactly one lecture now. But, I mean, while we've noted some peculiar properties of the Schrodinger equation, such as the fact that solutions to it satisfy the property that the probability derived from their indefinite integral from minus infinity to infinity of their modulus squared does not change over time, which is exactly what gives solutions to the Schrodinger equation their own meaning by Born's probabilistic interpretation. But now we look at the Schrodinger equation again, and it makes you wonder, I mean, it feels hopeless to actually solve this thing, right? How do we even approach breaking it down? So writing the full thing out, you get partial x squared psi plus u psi. I mean, it seems hopeless, our chances of actually solving this, right? Well, let's see if we can obtain even a primitive solution. So, the very first thing we do when solving weird partial differential equations like these is try separation of variables. So, we're going to assume, and this would be a very stupid assumption, you should realize why this is very dumb, that this is equal to f of x g of t. It can be factored into a function of position and a function of time. Now, we plug that back in here, and what do we get? We get minus I h bar, partial t of psi is f of x g prime of t, and that's equal to h bar squared over 2m. This will just be f prime prime of x g of t plus u psi, which is just u f of x g of t. And now things seem even more hopeless. And things are made only worse by the fact that you realize u is the potential a function of x masquerading as a constant. So really, we've got this nearly unsolvable equation. Or is it? Well, what happens if we divide both sides by f of x g of t, which is psi, now? What do we get? Well, you'll notice that the factor of f of x here cancels out, which means this side is a function of t, and the factors of g of x here cancel out, which means that this side is a function of x. Yes, u is a function of x as well, otherwise this would be doomed. But let me ask you something. If a of x is equal to b of t, can either of them not be constant? Well, let me ask you something else. What happens if you take the partial derivative of both sides? Of course, this goes to 0 since it's dependent on t instead of x, and this just becomes a prime of x. Oh, what? Would you look at that? Oh, wait, would you look at that? A of x is a constant. And by that logic, that means b of t is a constant as well. That's right, any function of one variable cannot be equal to another function solely dependent on a different variable unless both of them are equal to a constant. Which means that we can actually rewrite this as two ordinary differential equations. I h bar o minus I h bar g prime of t over g of t is equal to c is our first one. And this one should be relatively easy to solve because it's just a linear differential equation. You subtract cg of t from both sides, and then you take the ansatz g of t is equal to e to the rt. R is some complex constant. You plug that in here. You get I h bar r is equal to c. So r is equal to minus I c over h bar. And hence, g of t is equal to e to the minus c over h bar it. And yeah, that's a sinusoidal equation. But the f of x equation is going to look a little different precisely because of this pesky u of x factor. So what's the f of x side going to be? Well, it's going to give us I h bar, sorry, no, wrong side, minus h bar squared over 2m f prime prime of x divided by f of x plus u of x, and then the other terms cancel out. And this is equal to c. So you multiply both sides by f of x logically, because this is impossible otherwise. You get this minus c f of x is equal to u. Is equal to u of x f of x. How do you even begin to solve this? Well, you can't. At least, not without knowing u. This is the time-independent Schrodinger equation. And this is the equation that determines all of the solutions that we can possibly get with human hands to the Schrodinger equation. So how do we solve it? Well, today we'll look at one simple example, and next time we're going to look at a few more. So what are we going to check out today? Well, one of the simplest examples. What happens if we take u of x to be an infinite square-shaped well? By that, I mean it's some radius from the origin, it's 0, but aside from that, it's infinity. And actually, you might recognize this as the limit of x to the n as n approaches infinity. Okay, so, well, I guess you could say maybe absolute value of x to the n. Because x to the n by itself, x to the n by itself doesn't have a defined limit. Okay, so how do we solve the time-independent equations with something like this? Well, I mean, it's got to be fairly simple, right? We just split it into two cases. What is f of x inside the radius, and what is f of x outside the radius? So, first, what happens if inside the radius? Well, you take this as equal to 0. And so, what happens then? Well, you have this very nice linear equation. Then, you're allowed to take the ansatz, e to the rx, plug that back in, and what do you get? H bar squared over 2m r squared plus c is equal to 0. So r is equal to minus c minus 2cm over h bar squared, square rooted, which means this becomes I. And so, actually, you can also take the h bar out. And so, that means that you can write f of x as e to the square root of 2cm over h bar ix. And so, what does that make the final solution? Psi is equal to e to the square root 2cm over h bar ix plus, well, what's the other exponential? Minus c over h bar it. And so, what do we get out of all of this? This is equal to, if we take the real part, and I'm not going to be taking the real part right now, if we take the real part, what do we get? In fact, no, not just the real part. No, let's take the real part. Okay. So if we take the real part of this, what do we get? this is going to give us, if we factorize it, this is going to be e to the I multiplied by this angle. And so this is going to be cosine of the square root of 2cm over h bar x minus c over h bar t plus I sine square root of 2cm over h bar x minus c over h bar t. And that's our wave function. Now, you might recognize it as something very familiar, especially if you take the real part. Doesn't this look like the typical cosine of ax plus bt wave that you normally see in, regent physics? This is why we call it the wave function, because the simplest solution to it is this cosine of ax plus bt wave. So that's the time-independent Schrodinger equation, and one of its simplest and most interesting equations. Thank you everyone for watching, and we'll see you next time. One of its simplest and most interesting, at the same time, solutions